Okay, guys, this is the mathematical example following the general video for the properties of the total differential that we're going to be using in this series on chemical thermodynamics. So we have this sample problem here, and we're asking if this function has a total differential. Okay, so we're saying, does the function z have a total differential? And if you remember the definition for our function z, it included two functions, one function m and another function n. Okay, so in the example, we're given m and n. So m, or the partial of z with respect to x at constant y, is equal to 10x y cubed plus 7. N is equal to the partial of z with respect to y at constant x, and it's equal to 15x squared y squared. Okay, so we're going to check the mixed second derivatives, because we said that the partial of m with respect to y at constant x has to be equal to the partial of n with respect to x at constant y. And that basically just requires that the mixed second derivatives are equal to each other. So in other words, we could say that if we take the partial of z with respect to x, and then we do that same thing with respect to y, that has to be equal to the partial of z. First, we're taking the partial of z with respect to y, and then we take the partial with respect to x. The partial of z with respect to x after we've taken the partial of z with respect to y. So it doesn't matter which order we get to the second mixed derivative. The mixed second derivative has to be equal. So like I said, it doesn't matter which order we take the derivatives in. And this is the necessary condition for the function z to have a total differential. So we go through the motions and we say that the partial of m with respect to y is equal to 30x y squared. And then we do the same thing for the other function, and we say that the partial of n with respect to x is also equal to 30x y squared. So we say that the mixed second derivatives are identical, and consequently this function z, this function of x and y, has a total differential.